Two people walk into the exact same brightly lit, crowded room. From the outside, they share the exact same environment. Internally, the sensory data they process is entirely different. A clinical diagnosis effectively names a pattern of behavior. It labels what a person is doing, but it fails to map the biological and sensory architecture driving those actions. We need to stop asking the traditional clinical question, why won't this person act normal? Instead, we must ask a biological question. What specific environmental variables is this nervous system actively detecting, correcting against, or trying to avoid? Under this framework, neurodivergent profiles, like autism, represent a highly responsive, high-information architecture known as a high-gain nervous system. A diagnosis names the behavior, but it is not a roadmap. Without identifying the underlying high-gain architecture, the primary drivers of those behaviors remain invisible. When someone melts down or shuts down, observers often label it an overreaction. That label relies on a false premise. It assumes the environment around them is neutral. The environment is an active, demanding load. Variables like thermal gradients, complex social rules, and the flicker of fluorescent lights all place direct regulatory pressure on the body. Every piece of incoming data creates sensory throughput. Processing that throughput, comparing, predicting, and inhibiting responses carries a physical, biological cost. Return to those two people in the same room. One system filters out the noise, processing only the most relevant signals. The other actively manages a massive, simultaneous throughput of light, sound, and social expectation. A system correcting hard against a strongly detected mismatch is operating exactly as a high-gain regulator should. The internal response scales precisely to the load the system is detecting. To understand how this load is managed, we can borrow the engineering concept of gain, which is simply amplification. Gain exists in two separate locations, and the distinction is critical. First is front-end gain. This dictates how strongly a system detects an incoming signal. When you turn up the front-end gain, the system captures much finer environmental patterns and minute changes that lower-gain systems completely miss. The second location is inside the control loop. Loop gain dictates what happens next. A system with high loop gain responds aggressively. When it detects a mismatch or a threat, it corrects hard and fast. This rapid response comes with a physical cost. The system tracks tightly, but it overshoots its target, takes much longer to settle back to baseline, and operates with a severely narrowed stability margin. The neurodivergent nervous system is incredibly responsive by design. It secures this massive capacity for high-resolution information at the strict cost of a razor-thin margin for stability. We need to clear up a major misconception here. Having a high-gain nervous system does not mean a person is hypersensitive to absolutely everything. Gain is modulated independently across different pathways, a concept called channel specificity. A person might run incredibly high gain on external auditory signals, like overlapping conversations, while simultaneously running very low gain on their own internal hunger or pain signals. In this framework, a neurodivergent profile is understood as the specific distribution of gains across different channels. It's a way to read the unique requirements of the system. High gain is a personalized map. Effective interventions must target the specifically overloaded channels, rather than treating the whole person as fragile. Moving from engineering to neuroscience, we see that the brain does not passively wait to receive the world, it actively predicts it. Through a mechanism called precision weighting, a high-gain system assigns massive importance to tiny errors in those predictions. Constantly updating these predictions means environmental noise never fades into the background. It is processed as highly salient data requiring an immediate active correction. This chart shows how that processing requires finite biological energy. Based on neuroscientist David Atwell's energy budget analysis, synaptic transmission and neural signaling consume actual physical metabolic resources. Masking distress, monitoring social cues, predicting environmental shifts, and inhibiting physical reflexes rapidly drain this finite energy budget until it is completely depleted. Attention and emotional regulation require metabolically expensive biological actions governed by strict physical limits. When a nervous system is forced to repeatedly exceed its regulatory bandwidth day after day, the architecture begins to fracture. This accumulation of chronic stress and constant physiological adjustment creates a hidden, compounding toll known as allostatic load. Because individual capacity is governed by this biological load, human ability is highly state-dependent. A person might easily complete a complex task on Monday, yet find it physically impossible on Wednesday. Neuroscience data from Amy Arnsten reveals why. High-stress signaling pathways actively impair the physical structure and function of the prefrontal cortex. The prefrontal cortex is the exact biological hardware required for executive control, cognitive flexibility, and behavioral inhibition. Telling a dysregulated person to try harder fails because the biological hardware required to execute that demand has been temporarily taken offline by their allostatic load. We can apply this high-gain metabolic model to one of the most severe clinical endpoints, autistic burnout. Researchers define autistic burnout as a state of chronic exhaustion and a severe loss of skills, driven by a prolonged mismatch between societal expectations and a person's actual biological abilities. The mechanical cascade is precise. High environmental noise meets high gain detection, triggering relentless, aggressive loop corrections that rapidly consume the individual's metabolic budget. As their stability margin collapses and allostatic load peaks, the nervous system physically shuts down non-essential functions just to survive. Burnout is the inevitable mechanical result of a system functioning beyond its sustainable biological capacity. This framework also redefines urgent safety crises, specifically autistic elopement and the high risk of wandering and drowning. The standard behavioral view defines running away as noncompliance or a lack of danger awareness. The regulation-first model identifies it as an aggressive biological drive. A child running toward a lake or a pool is executing a high-velocity drive toward a powerful, necessary regulating channel. Water provides immediate physiological stabilization. The buoyancy, massive thermal shifts, deep pressure, and the triggering of the bradycardia reflex are tools a depleted nervous system aggressively seeks out to restore its loop margin. True safety intervention identifies the specific biological need the system is desperately seeking, meeting it safely before a crisis point is reached. Locked doors alone are insufficient. Applying a regulation-first roadmap changes the focus of support across clinical, educational, and family settings. The objective is never to turn the system down or force a neurodivergent person to normalize their external behavior to make others comfortable. Instead, the mandate is strictly environmental. We must reduce preventable sensory load, design predictability, and fiercely protect a person's metabolic recovery time. Success means engineering an environment where high-precision, high-gain architectures can operate safely within their stability margins, allowing their incredible sensitivity to function as an asset.